Let's wrap up section 2.3 with a little more practice with these new set operations. Remember, in this section we've learned complement, intersection, and union. And we've also learned how to use a Venn diagram to visually express the relationship between two sets, which can help us to solve these problems. Example 7. Let U contain elements 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Set A contain elements 1, 2, 6, 7, and 9. And B contain elements 0, 1, 4, 5, 7, and 9. Find the requested set and list it in roster notation. Now, one thing you might find helpful in working a problem like this is before you find all of the sets to go ahead and construct a Venn diagram that shows where all of the elements belong. So I'm going to sketch one out up here. This is going to be my set U. I'll have two circles, sets A and B, and I'm going to draw them so that they overlap. That'll be set A. And this will be set B. Make it a little bigger so I can see the overlap. And then I want to list where each element belongs. And remember, you're going to start in the innermost region and work your way out. That innermost region there is the intersection between A and B. So I need to figure out, what do A and B have in common? So I'm going to compare the two sets and I'm going to identify which elements they have in common. Looks like 1, 7, and 9. So those values go in the intersection, 1, 7, and 9. Now, everything that's left over in A is inside circle A, but outside circle B. And everything left over in B is going to be inside circle B, but outside circle A. And then finally, we have to figure out which elements in the universal set, that is digits from 0 to 9, have not yet been accounted for. So I'm going to look at the elements I have, just count my way from 0 to 9. If I see one that's missing, I'll write it outside circles A and B. So we have 0, 1, 2, looks like we're missing 3, 4, 5, 6, 7, we are missing 8 and 9. So now we have all of the elements of the universal set organized in how those two subsets relate to each other. The Venn diagram will make it easy to find the requested sets. So the first one we're looking for is A complement. That's going to be everything outside circle A. So I'm looking at circle A and I'm staying outside of that boundary. We have 0, 3, 4, 5, and 8. B complement will be everything outside of circle B. So again, do the thumb trick, right? Take your thumb, cover up everything in circle B, and then list everything outside of circle B. We'd end up with 2, 3, 6, and 8. Everything outside of circle B. 2, 3, 6, and 8. Next, we have A intersect B. Remember, intersection represents and. I'm looking for the elements that belong to both A and B at the same time. I'm looking for, what do A and B have in common? So we're looking at the elements in the intersection. The intersection is the overlap here between A and B. We've already found those elements. They are elements 1, 7, and 9. Next, we have A union B. Remember, we learned that represents OR. So I'm going to take everything in A and unite it together with everything in B. So I'm taking everything inside both circles. And I'm going to try to get them in numerical order here. Get some more room down here. So we need 0, 1, 2. Notice 3 is outside both circles, so I'm not going to include that. 4, 5, 6, 7, 8 is also outside both circles, so I'll exclude that, and 9. So in the union, we take everything in A together with everything in B, and I'm just ordering them for the roster notation. Okay, pretty simple so far. Let's look at example E. A intersect B complement. Notice A intersect B we have already found over here on example C. We got values 1, 7, and 9. We need the complement. That means everything except 1, 7, and 9. So that would be 0, 2, 3, 4, 5, 6, and 8. Example F, we have A union B complement. Remember, A union B we have already found down here on example D. Since we're looking for the complement, I'm going to list everything that is not in this set down here. So 0, 1, and 2 are accounted for. Again, I'm looking down here at this set, and I'm identifying elements that are missing, right? So 3 is missing, and 8 is missing. Now, if you want to see this on the Venn diagram, you can look at your illustration up here. Notice that A union B is everything inside both circles, right? So everything within that red boundary, including the intersection. Well, if I'm looking for the complement, that means I'm looking for everything outside both circles, and I can see those values over here, 3 and 8. Okay, let's try another one. A complement intersect B complement. Now, in order to do this, in order to figure out what A complement and B complement have in common, I have to know what's in this set and what's in that set. And we've already done that, right? We're looking over here. A complement was this example. B complement is this example. So I'm trying to figure out what those two sets have in common. So notice they both have a 3 and they both have an 8. So A complement intersect B complement contains elements 3 and 8. So again, we're building off the work that we've done before. Next example H, A complement union B complement. So in this case, to unite those two sets, I have to know everything in this set and everything in this set. And again, we have those listed over here. For union, remember that goes with the word or. I'm going to take everything in those two sets and make a new set, right? I'm uniting those two sets. So I have 0, 2, 3, 4, 6, 4, 5, 6, and 8. Unite the two sets like combining two classes. Okay, next example. We want A complement intersect B. All right, so I need to know what is in both of these sets. A complement is listed over here. That was the first set we found. And set B is up here. So I'm looking at A complement and I'm looking at B. And I'm identifying what do these two have in common. So again, comparing this set that we found here with B in the original listing, what they have in common. 0, 4, and 5. And those are all of the common elements. Next, let's work on A union B complement. Okay, set A, I need to look at it up here. So I'm going to consider set A, and I'm going to compare it to set B complement. Right? We are looking for the union of those two sets. So I'm simply going to join those two classes together and list everybody in the new class, right? So that's 1, 2, 3, 6, 7, 8, and 9. So my strategy here is to look at the set on the left and to look at the set on the right, and then use the operation for the signal of how I combine those. In this example, we found out what the two sets had in common. In this example, we just united the two sets. Let's try the next one. A intersect the empty set. So I'm trying to figure out what set A and the empty set have in common, right? Remember, the empty set is empty. It has no elements. Therefore, it cannot have anything in common with A. So A intersect the empty set is empty. There's no elements common to A in the empty set. On the other hand, if I take set B and I unite it with the empty set, I end up with everything in B, right? If I take everything in B together with nothing, I end up with everything in B. Let's see if we can answer the last few questions. Is A intersect B complement equal to A complement intersect B complement? Well, let's go find those sets because we've already done the hard work. A intersect B complement is this set right here. And A complement intersect B complement is this set right here. Comparing those two sets in roster notation, are those equal? Clearly, the answer is no. Okay, so what I want you to notice here, what's being illustrated, is I can't distribute that complement, which is what's been done over here, and get an equal set. So set complements do not obey the distributive property. Let's try the next one. A union B complement, that is this set right here. We want to know if that's the same thing as A complement union B complement. Well, we did that right here. If I compare those two sets in roster notation, I can clearly see they are not equal. So once again, we need to observe we cannot distribute a complement, which is what seems to be happening here. Next question. Is A intersect B complement? Well, let's find A intersect B complement. Is that the same as A complement union B complement? Well, let's look at A complement union B complement. If I compare item by item, I see that they have exactly the same elements. Therefore, those are equal sets. Now, notice what happened. We did distribute the complement, right? A has a complement and B has a complement. But notice the intersection turned into a union. That's kind of interesting. Let's answer one more question. Is A union B complement? A union B complement is over here. Is that equal to A complement intersect B complement? That is this set right here. Clearly, they have exactly the same elements. Therefore, those are equal sets. So make the observation. When you distribute a complement, the sign switches direction. Later on, we will officially name those as De Morgan's laws. They will be important for set theory, and they will also be important for logic. This completes section 2.3. Please practice complement, intersection, and union. Those operations will be relative to set theory, logic, and even probability in chapter 11.